All right. Hello, everyone. My name is Bruno Ribeiro, and I would like to welcome everyone to the seventh presentation of the webinar series called Nowcasting Operations and Techniques, Perspectives for South America. And this series is supported by the Nowcasting and Mesoscale Research Working Group of the World Weather Research Program of the WMO. And we would like to thank all the individuals who have registered for today's talk. And the series consists of webinars that are normally broadcasted live at 18 UTC on the first Friday of each month. And the presentations are recorded and made available in the YouTube channel of the Department of Atmospheric Sciences of the University of São Paulo. Today's speaker is David Sills. His talk will be followed by question and answers sessions afterwards. We'd like to ask the audience to place your questions in the Google Meet or in the YouTube chat, and we will read your questions right after the presentation. And please, for those in the Google Meet session, remember to keep your microphone muted. And now I'd like to pass the word to Rachel, who is co-chairing the webinar presentation with me and who will introduce today's guest speaker.
Thank you, Bruno. Hello, everyone. I'm Rachel Albrecht from University of São Paulo. It is my pleasure to present our speaker today, David Sills. He earned his PhD in atmospheric sciences from York University in Toronto back in 1998, and he served as a severe weather scientist at the Environment Canada for more than 20 years before becoming the executive director of the Northern Tornadoes Project with the Western Engineering in 2019. Dr. Sills is also an adjunct professor at both Western University and the University of Manitoba. In 2017, Dr. Sills was awarded with the Rube Horston Medal for his contributions to operational meteorology in Canada. He currently serves on the American Society for Civil Engineering Committee, developing a new enhanced Fujita scale standard, and recently completed a 4-year term on the Nowcasting and Mesoscale Research Working Group of the WMO. Dave, thank you very much for accepting the invitation for this webinar, and the floor is yours.
Great. Thanks, Rachel. Thanks for the introduction, and thanks for the invitation. It's great to be here to present this information today. So let's see if I can handle all of the technology. Give me 1 second. Okay, so now you should see my screen. Is that correct, Rachel?
Yes.
Great. And I even have a little laser pointer here. Okay, great. So I'm going to be talking about the Northern Tornadoes Project, which is something we've undertaken here in Canada, and it's helping us to better understand severe local storms in Canada. And I'm the executive director, as was mentioned. I'll get into a little bit of why this project came about. And this is a map of, well, number one, it's a map of all the tornadoes that were known across Canada between 1980 and 2009. And you can see the colors of the F scale. This is pre-EF. But all of the reports are in areas where it's urbanized in Canada. Almost all of our urban population is right along the border. Some of it extends up into middle of Alberta here. But we get lots of thunderstorms outside of these areas, in this area that is outlined in red. And we know there's severe weather occurring there, but we just don't get any reports. So we know that we're missing quite a few tornadoes in these areas. And it's important because there's a lot of infrastructure. There's electrical infrastructure that comes down from dams up here. In some areas, there's some nuclear power plants and so on. So it's important to know the entire picture. One of the things we did to try to get a better idea of what should be happening is we built a statistical model using that observational data and also lightning and population density. And the modeling showed that instead of 62 or so tornadoes a year that we had on average in Canada, we should be seeing something closer to 150 tornadoes per year. And it really fills in a lot of that northern area where we know there's likely tornadoes occurring, but we're not getting any reports. And a couple interesting things is this is the Rocky Mountain area. So clearly there's a gap there where over the mountains that seems to be real. And there's this gap here, which is to the northeast of a big cold Great Lake called Lake Superior. And we believe this would be real as well, just because the cold lake really suppresses convection downwind. And it really divides the number of tornadoes into two areas, one in Ontario and Quebec here, and then one across the prairies in the western part of Canada. It also showed that the maximum number of tornadoes should be occurring in the kind of the middle part of the country here in southern Saskatchewan. So we were definitely eager to see if all of these statistical assessments would be borne out in the data. And we actually formed this Northern Tornadoes Project in 2017 at Western University, but in a very unique situation, the funding was provided by a social impact fund called Impact WX. And they wanted to know what the tornado climatology was across Canada. So we're willing to fund us to do this work. And it's probably not funds that we would get through grants. So it's good that we had this funding organization. And actually the organization is run by a very interested person who does in severe weather, who does storm chasing and that kind of thing. So it's clear that's where they wanted to focus their attention. So another unique thing about the Northern Tornadoes Project is the core team is composed of both meteorologists and wind engineers, and that's kind of unusual. Usually it's one or the other, and they don't mix too much. But definitely our group, you can see at the left here, is composed of both meteorologists and wind engineers. Greg Kopp is the research lead on the project, and he's a wind engineer, and I'm the executive director meteorologist. And then we've got a set of people that work for us that are that as well. We have strategic partnerships with the University of Manitoba, York University, a cable news channel called the Weather Network in Canada, Instant Weather, which is a social media aggregator type of site, CatIQ, which is a insurance type of site or institution, and we closely collaborate with Environment Canada, which is the government weather service here. So our goal is to advance the knowledge of the true tornado occurrence and risk across Canada and find all those missing tornadoes. And so for every tornado that occurs across Canada, we want to detect, assess, document, make public all of the tornado data. And again, we can use this to build our climatology, to build risk assessment, and do assessments about the influence of climate change. And there's also research that goes on that is necessary to improve the event detection. So even as we're doing the detection, we're working on research to further improve the detection, because there are challenges with trying to detect tornadoes in forests and tornadoes in croplands and that kind of thing, where there's not a lot of damage indicators. But we're also doing research to improve the way we do things through automation. So for instance, instead of having one of our staff go through and mark off every tree that's been down in a big satellite image or a big drone image, we actually have tools now that will go do that and take that tedious work. And for the most part, about 80% of the work is done through automation now, and the rest is just some corrections by the operator. So we're heading in that direction. It's great. I titled this, "When You Go Looking for Tornadoes, You Find Other Things." So we follow up on all reports of wind damage and look for, and NTP looks for wind damage along the path of intense storms. So some of our data sources, of course, social media. We get lots of reports from social media. We have partners that are social media aggregators and actually will go through all of their thousands of reports that they get and send us the best ones. So a lot of times the events that we know about because of social media. We also use tools like the US multi-radar, multi-sensor suite, which puts radars together from across both countries, US and Canada, so we can see things like hail tracks and storm tracks and rotation tracks and these kinds of things that help us know where the storms went. And of course, during events, we're watching radar in real time. And this is an example of a supercell that went through our nation's capital in 2018 and caused an EF3 tornado, and lots of havoc there. And we were able to follow that in real time, and then right away be able to send crews out where damage had occurred. But as far as looking at it after the fact, we have a number of different technologies. One is we use planet.com to use their satellite imagery to find tornado scars. Now they have their own constellation of microsatellites, and they do daily high resolution sampling across the globe. So if we have an event that we think occurred, we can look at the satellite imagery just before and just after the event, flip between them, and then something like this will really pop out, a long narrow track associated with a tornado. If we're doing a damage survey and we don't have access or road access, then we can put an aircraft up, and that will get us 5-centimeter imagery. This is from the early days when we were doing it for every event, and there were roads there. But most of the time, it's in events where we can't get to the area on road. When we can get to the area by road, we're doing ground surveys. So the wind engineers are looking at the buildings and the components and getting all the details about the bolting and the nailing and how the building came apart, how far did missiles travel, and so on. But we're also running drones, and that gives us very high resolution data. So this is down below 2 centimeters in resolution. And at this point, we're able to see all the directions the trees are down, the root ball, even the species of tree. And more, we're gathering drone data and relying less on getting aerial data where possible. So a lot of effort goes into classifying this wind damage. Is it due to a tornado or is it due to downburst? And I'm sure you probably know the difference between a tornado and a downburst, but I'll go through it. So with a tornado, you've got a violently rotating column of air that goes from the lower part of the thunderstorm to the surface. And it can be over land or over water. We do count tornadoes over water or water spouts in our statistics. And the vortex is often made visible by a funnel cloud aloft and dust and debris over land, or a spray vortex over water. Whereas a downburst, it's damaging storm downdrafts caused by precipitation, evaporation, and loading. And so the damage patterns from these things are quite different. With a downburst, you've got air coming down out of the thunderstorm and spreading out. So you'll have divergent damage indicators in a forest, say. Whereas with a tornado, the wind is going in towards the tornado area and then up into the thunderstorm. So you'll have convergent damage indicators and usually a long, narrow path. So that's basically what we use to determine the difference between tornadoes and downbursts. Although we've developed a lot of different tools and rules of thumb to do that as well, but that's the main difference. So since 2017, the start of the project, we've identified 588 tornadoes and 351 downbursts. And sometimes they're both with the same event. We had one strong tornado that had 33 microbursts along either side of it that we were able to analyze. So that was a very interesting event. And if the swath of wind damage from downburst is at least 650 kilometers long and 100 kilometers wide, then we can call that a derecho. And we've had our first derecho that we investigated, that NTP investigated, happened last summer, or actually in the spring. It wasn't even summer yet. So I'll talk about that as well. So I'll be talking about tornadoes, downbursts, and derechos. Before I do that, all our data, as I said, we publish and we make it open so people can access it, right from researchers to industry to the general public. There's a lot of interest in this, and it gets a lot of visits. Our dashboard gets a lot of visits. This dashboard is hooked up right to our GIS backend, and you've got all these filters on the side here, the descriptions of what each of these things is, and then you've got the actual plotting itself. And this is all of the events in our database from 2017 to 2022. And so over that 6-year period, we've got 1,352 events that are recorded. So a combination of downbursts, tornadoes, and other things, such as dust devils and that kind of thing. And tornadoes make up 588 of those events. And again, you can see the clustering here in Ontario, Quebec, and then over the prairies as well. And I'll talk about that a bit more. So tornadoes. These are the tornadoes we experienced last year. Nothing above EF2, thankfully. But you can see that most of the tornadoes occurred in kind of the interior parts of the country, not off in the oceanic coasts and not off in the Arctic. We had one waterspout way up in the north of Saskatchewan here, but most of it was down in the south here. 29 of them were EF2s, but 117 tornadoes overall, and that is actually the highest number of tornadoes that we've recorded in Canada to date. So we're clearly finding a lot of these missing tornadoes. 11 of them were tornadoes that were over waterspouts, and a lot of those happen over the Great Lakes, especially in the fall when you've still got warm water but cooler aloft. And I'll dive into one of the tornado events from this summer. This was July 24th, and this is what we call an event summary map. So all of the layers of data that we collected can be turned on and off. You can see the 514 drone photos, 79 ground photos. The text summary of the event is over here. And this was an EF2 tornado that had a path length of about 56 kilometers and a maximum path width of 1.4 kilometers. So this was a beast of a tornado that went through in eastern Ontario. So this shows where all of the ground and drone photos were taken. It shows the tornado center line in black here. And then this arrow points to where the worst damage occurred, where this pin is, and that's the damage rating is EF2. So that's how these event maps are arranged. But if we drill down, we can get into the drone orthomosaic that was put together for this particular event. And so again, this is the drone flight, but in this case, the drone flies a grid pattern, collects thousands of images, strings them all together to come up with this orthomosaic that's high resolution. And all of these orange points are just single pictures from the drone. So you've got this orthomosaic plus the single pictures, and then you've got the ground photos as well. And let's see if we can dive in a bit more. Let's go down to this area here. And here we see a really high resolution image from the drone that shows clear evidence of rotation in this case, where the trees are coming from the south here, and then over from the east here, and in from the west here. It's all a big mess in the middle. This was a multi-vortex tornado. So there are a number of these kind of rotation marks along that long 56-kilometer path. And here I'm showing all of the tornadoes that are in our database, just the tornadoes from 2017 to 2022. And with the idea that if you remember back to our statistical map, it said that there was likely going to be a gap in the data over the mountains, and we certainly see that. There was going to be a gap downwind of Lake Superior because it's so large and cold, and we are certainly seeing that. There hasn't been a single tornado in that area. It just really shuts down all thunderstorm activity in that area in most severe setups. And again, the maximum tornado frequency was supposed to be in southern Saskatchewan. And that's one of the things we haven't really seen so far. It's been fairly quiet in the last few seasons in the prairies, and we're getting far more tornadoes occurring in the east. You can see that there in Manitoba here, there has been an EF3 and even an EF4 tornado. But there's just the number of tornadoes in especially the eastern part of central and eastern part of Ontario and into Quebec, near Montreal and Ottawa. Lots of activity there. And we're not sure if that's something that's a shift that's going to stick around, or if that's just happened in these last 6 years or so. So, we're collecting all of this data. We're in it for the long haul. We'll be collecting the data for a long time, and we'll be able to pull out some of these trends eventually. But in the meantime, we're collecting very high quality data every year. And we have also got a new advanced dashboard that we're working on, targeted towards advanced users. So this includes tornadoes that go back well before NTP, back to 1980, which was the beginning of the first 30-year climatology for tornadoes. And then includes tornado tracks were available. So you can see this is Eastern Ontario and Ottawa here, and all of the different EF2, EF3 tracks. Some of them are fairly long that have occurred in this area. And we'll have even more extensive filtering capabilities to really isolate certain combinations of parameters and get down to maybe why some of these patterns exist, why there are certain clusters here and not here, and so on. Okay, moving on to downbursts. So while we're looking for tornadoes, like I said, once we have to classify the damage as either tornadic or downburst, we're ending up with quite a collection of downbursts in our database. So just in this year, 94 downbursts recorded, some of them up to EF2 in strength. That was with a derecho, and I'll talk about that in a bit. And we're still bringing in some more data, so there'll probably be more than that in the end. But again, pretty much across Canada, we're seeing lots of downburst activity. This is across the 2019 to 2022 period. This is the first year we started recording downbursts. So 351 downbursts. So we're getting quite a good data set of downbursts across Canada. And again, you can see it's very similar to the pattern for tornadoes. Maybe a little different in certain places. One thing that sticks out is these 34 downbursts that occurred over a couple days in 2021. And that was associated with a really anomalous heat dome that set up over the Pacific Northwest. And these thunderstorms occurred along the northern edge of that heat dome. So it's fairly unusual to get such strong thunderstorms and downbursts way up in the northern parts of British Columbia and Alberta, and even into Northwest Territories. And I'll get into that a bit more. We actually did flights over these areas, aircraft flights, and everything in red. It's hard to tell what is and what isn't damage here, but most of this is damage over very large areas. And if we zoom in on this one particular area, you can see that every tree is down. And yeah, it's with a downburst, we're expecting trees to be all down in the same direction. But when you get into clusters of downbursts, you get kind of fanning areas that fan out and then overlap, and that results in some areas where it appears to be convergence. So we do have to be careful when we're analyzing this, that the convergence we're seeing is actually one microburst interacting with another microburst rather than a tornado. But it's very clear if you don't have a long, narrow path, then you don't have a tornado, but very impressive damage. And on to derechos. So I mentioned that we had a derecho last spring. It was May 21st. There were several downbursts that caused EF2 damage with wind speeds to 195 kilometers per hour. So really impressive. The storms themselves were moving 100 to 120 kilometers per hour. The max recorded wind gust is 131 kilometers per hour. So one unlucky weather station got the big gust there. There was a continuous damage path that was about 1,000 kilometers long and about 100 meters wide. So definitely fits the definition of downburst. And the MCS, the mesoscale convective system that caused this, actually lasted over a period of 9 hours. It caused 12 fatalities, at least 12 injuries. It's the deadliest derecho in Canadian history. Over $1 billion in insured losses, and it's now the 5th most costly natural disaster in Canadian history. So just a huge event. And because all of our population is kind of located within 100 kilometers of the U.S. border for the most part, This derecho went right through one of our most populated areas. It affected 41% of Canada's population, which is just incredible. So this was really an extreme thunderstorm event. And, it took months for us to map out all of the damage. The yellow outline here is basically the radar reflectivity where the MCS existed on radar. The light blue is where we're seeing EF0 damage. So you can see that long path over 1,000 kilometers going right through our most populated region there. And then you get into EF1 damage, EF2 damage, and there were also tornadoes embedded here too. There were a couple tornadoes in London where I live, and I investigated those. And then we had a couple EF2 tornadoes that were closer to Toronto from this system. And it actually started in the US and ended in the US, but they don't seem to be as interested in this event as we are. So because just hardly any damage occurred there, but definitely one of the biggest events in Canadian history. And just to, again, go look at some of the raw data here. This is another event summary map, and we're looking this time at downbursts that affected the Ottawa area. And we can drill down and see we collected orthomosaic here, orthomosaic data here with the drone. And you can click on any of these blue points, and that brings up the ground survey photo. So in this case, it's a house with damage. And then if you zoom into that orthomosaic, you can see this is the kind of damage that was experienced in that area. And again, you can drill down even more, click on one of the points in that area, and there's one of our survey interns standing there for scale and among all of these damaged, snapped, and uprooted conifers. So that's what's available to the public. They can drill right down to all of this high resolution data and right to our photographs. So everybody has access to this. The warnings for this were very interesting because, well, number one, the numerical models did not pick up on this event. I mean, none of them. The medium resolution, the high resolution, the convective scale resolution just did not pick this event up. And it really started getting warned once it started causing a bit of damage down this way. And they had a warning with gusts to 100 in the warning through to this location here. And then there was a gust. That gust to 131 kilometers was about here. And that's when they started taking this a bit more seriously. And in fact, they just had enacted a new extreme thunderstorm alert that if there was a gust over 130 kilometers an hour or hail over, I think it's 7 centimeters, then they can issue this extreme thunderstorm alert, and that actually goes broadcast intrusive. So they did that for the very first time with this storm. And the gray dots are injuries, the black dots are fatalities. And you can see that's, right where they're issuing those warnings is right where a lot of the fatalities were occurring. They, for some reason, thought the storm would dissipate here and lifted the extreme thunderstorm warning. There were still some deaths that occurred, but then it picked up again. And a lot of the fatalities occurred in the Ottawa area where they did have the extreme warning issued. And the electrical infrastructure in Ottawa was really severely impacted. There were people in the city that didn't get power back for a week. So a big event. And of course, everybody wants to know, well, how rare are these things? And we really didn't know. We didn't even have an official list of derechos affecting Canada. So I went back and applied the criteria for a derecho and found how many had occurred in the past, and got back to 1922 in the prairies here was the first one in our database. But you can see a lot of them cross the Great Lakes region. Most of them kind of go from west to east and then dive down toward the southeast, because the heat dome that they're riding over top of is usually over the central U.S. But in some cases, like in last year, the heat dome was over the east, and that actually rode over from the southwest and rode over the top of it that way. And again, that goes right through our most populated region. So still building this climatology, but it's certainly informative and helps us understand and put in context this event that happened last year. So a bit about the future with the Northern Tornadoes Project. we are not only collecting data in the current year, but we're also extending our databases backward and try to improve the quality of existing databases. And one of the things that we're working on is an updated 30-year climatology of tornadoes. The previous climatology was 1980 to 2009, and this new one will be 1991 to 2020. And so that's roughly what it looks like. And the interesting thing is comparing it to the last climatology. So these graphs show the tornadoes by month across Canada in the new climatology. And everywhere across Canada, the peak month is July. It's nothing like the Tornado Alley in the US where the peak month is in May. It's July, that's the big month in Canada. And if you compare that to the old climatology, what we see is a lot of the prairie tornadoes, so that's the green and the blue, they're starting to decrease. And the orange here and the purple actually are increasing. And that is that effect of less prairie tornadoes and more Ontario, Quebec tornadoes. And so it does show up in the climatology difference between these two different 30-year climatologies. And again, we don't know if that's a long-term trend. I think we're going to need one more 10-year or one more 30-year climatology in 10 years to be able to say, hey, that's a trend. And then there's, why is this occurring, and does it connect to climate change? So there's all kinds of questions to answer, and it all requires high quality data, and that we'll just keep collecting that. One of the interesting things is in Southern Ontario, where I am, we have the longest and best quality database for Canada. And so the data extend all the way back to Canada's first tornado in 1792. But the data start to become usable for this kind of thing starting in about 1875. So we looked at data from 1875 to 2019. And if you look at all the tornadoes over that period in Southern Ontario, there's definitely an increase in the number of tornadoes that we've got in our database. But if you just filter it by only strong and violent tornadoes, so anything EF or EF2 plus, there really hasn't been much change. It's fairly flat. So what this is telling us is that we're recording a lot more of the weaker tornadoes, and that likely is due to non-meteorological factors such as just a more general interest, a heightened interest in severe weather, social media. The reports are getting out to us, people being able to take more photos and video with their cell phones. All of this technology is really changing the number of weak tornadoes that are being picked up and reported and counted. But if we just look at those tornadoes that we know are stable over the last more than a century, what we do notice when we look at the statistics of it is that they're occurring later in the year. It used to be that tornadoes, the stronger tornadoes in Southern Ontario, would happen earlier in the year in May and June, maybe July. But we're starting to see tornadoes occurring in August, even into September. Some of the bigger ones have occurred in September just in the last few years. And that's statistically significant. What's interesting is that there's no similar trend for neighboring U.S. states of Michigan and New York. So we're trying to figure out why that is. It might have a connection to climate change as far as the Great Lakes we know are warming due to climate change, and Southern Ontario is surrounded by these warm lakes. So that might be what's going on, but we have a lot more work to do to try to figure that out. I'm not sure if you're aware, but we started a kind of a sister project called the Northern Hail Project. And this started last year. It was a pilot year last year. And this is insurance-funded field work. So it's not the donor-funded model that we're using with NTP, but it's insurance-funded and grant-funded. And it's the big hail problem in Canada is in the province of Alberta out west. There's billion-dollar hailstorms. So that's where the work is focused at the moment. There's a 5-year field project. But like NTP, this will involve operational hail data collection across the country and documenting events and making it available in open data. So initially, what the main research activity is actually real-time collection of hailstones by a chase team, slowly following these severe storms and then documenting the storm characteristics. And actually, in the very first year, they were able to find Canada's largest hailstone, which was 12.3 centimeters in diameter and 293 grams. So record hailstone in the very, very first year. And I have a feeling that we may have record hailstones every year now. As you know, the fact that you're looking means you're going to find things like this. Something else we're working on is we're working with that instant weather aggregator on a radar app. And the reason for this is that the radar tools that are available from the government weather service for our radar network here aren't very good. And even within the weather office, they're not very good. So we're developing a new processor and a viewer, and that's pretty much complete. Here's an example of a case where you've got the reflectivity and you've got the velocity, the radial velocity, and you can take the swipe tool and swipe back and forth, which is really neat because you can kind of very easily co-locate things like hook echoes and rotation due to mesocyclone and that kind of thing. The idea is it's being beta tested right now, but it'll be available to the public and to the weather office. Hopefully they'll use it too, via subscription starting this spring. And one thing that we're doing is using it for the field work with the Northern Hail Project. So here we brought in the multi-radar, multi-sensor mesh, the maximum expected size of hail. I think that's what that stands for, which is gridded, and we can bring it in real time. And the people out in the field can actually see this and know where to go relative to the big storms. The interesting thing is, you know, you would think with these the big mesh numbers out here, that's where the record hail would have been, but actually the record hail was found here, and it kind of indicates there may be a bit of a disconnect between the mesh algorithm and where really large hail is occurring, and that's something we definitely will be investigating through further field work. And this may interest you, is the next steps for this radar app are adding storm tracking, severe weather detection, and intensity nowcasting. And we want to do this through a community open source approach to algorithm development and testing. So we want people to contribute to it. Obviously, it'll be based on the latest science, but we also want it to be available to the community and have the community, you know, actually help us improve it. So, you know, it's a different model. It's a community model, and it hasn't been tried before in Canada or even the United States, as far as I know. So we'll see how this works, but I'm really excited about it, and I'm hoping that this is going to really take off. And I think this is the last thing I'm going to talk about. We have a grant application submitted for a severe convective storm detection and nowcasting testbed, and this is really the area of focus for the Northern Hail Project in here. And so this is why the test bed is going to initially be here, with the idea that we're going to put a dual pole Doppler C-band at the center of this network, and then have 9 super sites located within radar range. And these super sites will have surface weather stations, hail disdrometers, lightning mapping array stations, coordinated field cameras. You know, we're going to throw everything we've got at it in here. And also we'll have vertical profiling, even some mobile weather stations to operate within the radar domain. And the idea is to really test new ways of detecting and nowcasting severe thunderstorms. The radars that we have across the country now, the new S-band network, really aren't optimized for severe storms. And so we want to make sure that what we're doing with this research radar is finding the best ways to detect and nowcast severe thunderstorms, and try to transfer that technology to the government weather service so they can start using that with our national network. And the idea is that this will be a portable network, and that after the 5-year project is up here, we might move it somewhere else, maybe the Eastern Prairies or Southern Ontario or something like that. So just to summarize, our understanding of Canada's national tornado climatology is, as I've shown, improving as we really detect, assess, and document every tornado that occurs. And I really think we're getting every tornado that is causing damage. It's a lot harder to get tornadoes that don't cause damage or very light damage, and we're probably missing some EF zeros, maybe some EF ones, but anything above that, I think we're certainly getting, and probably most EF ones as well. And while investigating these tornadoes, we also find downbursts, and for the first time a derecho in 2022. So we're generating those data sets as well. And this all leads to improved severe local storm climatologies, and you've seen how we can use those. And that's it. I will
Thank
it out.
Thank you, Dave. It's, great talk, and it's really, really good to see that it's actually kind of getting like children projects out of the Northern
Right.
Tornado Project. It's expanding on the experience that you all have. So now we open for questions and answers. If somebody has one, you can post here on the chat. You can also put the question in Portuguese if you don't want to do it in English, and then we will translate, or Spanish also. Those are the languages I can do.
I can do that, but I can't.
And also on YouTube. Bruno, did you see any questions? Not so.
No, none so far. I can start with one, I guess, and then we wait for more. So yeah, nice talk, Dave. Can you talk a bit more about the statistical model that you used to estimate the number of tornadoes in the beginning of the talk?
Sure. Yeah, we were. There's been a lot of work on trying to fill the gaps in tornadoes, especially in the U.S. And they usually use things like population density and pretty much non-meteorological fields to try to fill those. So we were trying to think of ways to use a meteorological approach, and we have this great data set with our lightning detection network that Vizsla runs in Canada. Has millions and millions of flashes, so lots of samples. So it's a high quality database. And I guess the assumption we're making here is that any thunderstorm has the potential to generate a tornado. And really, I don't see a good reason. There's not like there's areas in Canada that have a preference for generating tornadoes without thunderstorms, except maybe the Great Lakes in the fall. That's kind of a special case. But I think that assumption holds up pretty well. And so we used all of that and used some fancy Bayesian statistics that the grad student that was doing the work did. Can't say that I'm an expert in it, but and yeah, we're able to really fill in those gaps using, it was mostly the lightning data that was useful for filling in those gaps. And so now we can collect data in those areas and see if what the statistical model has shown us is realistic. And initially, I think the first year we ran nationally in 2019, I think we got 70 something tornadoes, which is half of 150 that we were expecting. So we were wondering if that 150 number was way too high. Actually, I thought it was low initially, so I'm surprised that we didn't get more in that first year. But as we have developed our skills in doing this work, and actually we've had a couple more active years in the last couple of years. So both 2022 and 2021, we have a total of 117 tornadoes. So that's getting a lot closer to 150. So I think the work that we did with the statistical model was really informative and allowed us a good idea of what to expect. And it's really something good to compare against as we collect more and more data. And that's published in a journal, by the way. It's peer-reviewed science.
Good.
Nice, thank you.
So here in South America, or most of the countries, or if not all of them, they don't have official agencies that are responsible for the severe weather reports. And also investigating if anything had happened. So basically, we as scientists, we also use social media for reports. And you mentioned that the project has social media aggregators. Can you explain a little bit more how that works?
Sure. Yeah, one of our partners is called Instant Weather, and they started out as a Facebook-based platform that they do. Basically, they're watching radar, looking for rotation signatures, and then sending out alerts to people, trying to basically get ahead of the tornado warnings, which they were very successful at, actually. And in the process, they built quite an audience, and all of these people that were coming on started contributing damage that was occurring in their area and photos of tornadoes and that kind of thing. So it started fairly small, but now they're up to 1 million subscribers on Facebook. And that's across Canada and the US. And so obviously with that kind of an audience, you're going to get a lot of reports. And so that's probably our main source of reports. And we actually have a special communication window just for communicating what they're seeing as far as reports coming in and where we're investigating. And so we're collaborating quite closely on that. And it's actually the same organization that's putting together this radar viewer and processor as well. So we're doing quite a lot of work with them.
Oh, that's great. It's a very good example of citizen science.
We've got interns that work with us every year, and one of the intern projects last year was coming up with a social media scraper. So we can, we can run this thing and try to get maybe some social media reports that we wouldn't otherwise find. We do pretty well with that, and we have a lot of enthusiasts that help us with that. If they see something, they forward it to us. So we're, during a storm, we're getting it's a fire hose of data coming at us from all different directions. But some of this is makes sense to automate. Some like I said, the tree analysis is one thing we've automated, and also trying to automate this scraping of social media, and we'll see how it does. We'll see how useful it is. But it's certainly a fun project for these interns we bring on.
That's great. We have a question from Jennifer Silva. Why do we have these gaps on the west side and over the lake?
Right. So the west side, I believe she's talking about the mountains. So that's where the Rocky Mountains are running through Canada, and it's pretty difficult for thunderstorms to make it across the Rocky Mountains. Sometimes they start in the foothills and try to get up and over, but they usually don't make it. And on the other side, they start up in the foothills and then progress into the east and into the greater moisture on the plains. But over the mountains themselves, the thunderstorms don't get very well developed, and tornadoes tend not to occur there. I mean, we are actually looking at all of the satellite imagery in that area and looking for tornadoes in that area. So it's not like we just can't see it there. I just don't think they're occurring in the mountains. And as far as the lakes, the Great Lakes, because of their size and because of their temperature, they're especially Lake Superior, it's an inland sea that's cold. It's like in summer it'll be less than 10 Celsius, and that really shuts down convection. Usually the convective regime for severe weather is southwesterly flow ahead of a cold front. So basically that southwesterly flow goes over the lake, and you get all of the cool marine air being blown inland, and really thunderstorms just don't have a chance in that environment. So not only do we not see tornadoes there, we barely see thunderstorms there. So and it occurs with all of the Great Lakes, although not to the same extent. Some of them are warmer, but you can definitely see this pattern to the lee of the Great Lakes, where there are fewer tornadoes, and in some cases no tornadoes that have been recorded to the lee of the lakes.
Even on the West Coast, right? I remember, like, it is like a fuzz when you see a storm, regular one, like lightning.
Right, yeah.
Very different from here.
We did have an unusual case in Vancouver, I think it was 2 years ago now, where the thunderstorm, that a supercell formed over the ocean and actually moved inland and caused damage with a tornado. So it can occur. It's just super unusual. So yeah, that was a bit of a surprise for the people out in Vancouver. Number one, to get a supercell thunderstorm, but also to get a tornado that ripped across the University of British Columbia campus.
Yes. Bruno, do you see the other question?
We have a question on YouTube. It's from Kleber Rocha. How many radars are you currently using to detect tornadoes or severe weather in real time?
Sure. There's the network of radars in Canada is 31 going on 32. They're all being upgraded to S-band, and that's mostly done now. And there are radars in the US that cover parts of Canada as well. So that's probably another dozen radars. So we were looking at something like 40 radars or so, where it's collecting data that's useful to us, and we have to go in and try to figure out where the thunderstorm went. And we actually we classify each tornado by its parent storm type. So if it was a supercell tornado or a QLCS tornado, land spout tornado, we try to record that. That's mostly based on radar data, just so we can start gathering some statistics. I mean, in Canada, it's not like the U.S. where they know so much about their severe weather. Here, we have no clue how many tornadoes are caused by supercells versus QLCS versus land spouts. So that's part of what we're doing, is gathering that data, and the radar is really useful for doing that.
And are these radars polarimetric radars that you have in Canada? Most of them are.
Right. Yeah. The new S bands that were put in, they're Leonardo, used to be Celex, and they are dual pole Doppler S band radars. So they're actually on par with the Nexrad radars in the US. In some respects, they're a bit better. They're just more modern, but it's taking a lot to get all the bugs, all the wrinkles out of the processing, and we're still working with the company, the vendor, to try to really improve the quality of data, especially in high shear areas like mesocyclones and that kind of thing.
Mm-hmm. Okay, I think we don't see any other questions.
No, there is one here from Tiago.
Oh,
Tiago. Yeah, Tiago is
on
part
YouTube.
of.
There's no one in YouTube, I guess.
Yeah, Tiago is part of the group, but he's only on YouTube today.
Okay.
In your opinion, the increased number of severe events in the last decade are probably more related to more observations than climatological changes? And there is a following up question. Is there any indication that those events are getting more extreme, or are they just increasing in occurrence?
Right. There's a lot of things wrapped up in that. Number one, our cities are expanding. There's more vulnerable infrastructure. People are building, in their basements, these fancy man caves and this kind of stuff. So when there's a flood or damage at a house, there's a lot more damage that's occurring. So the insurance industry is telling us that the amounts are going up and up, but part of that is just the increasing vulnerability of society. As far as the tornado numbers, yeah, they're definitely going up, and since we've started this, and that we're actually working backwards now, so those are going up as well too, and we know that's due to us putting in the extra effort to find these tornadoes, but we're also working on methods to try to take out that bias and compare tornadoes across longer periods, like I did with that Southern Ontario study. So there are ways to kind of treat the data so that you can remove some of these human factors that are in there. To date, we haven't been able to connect any changes to climate change, or even just finding the trends is difficult with the data that we have. And in the U.S., I mean, they've got 10 times the tornadoes that we do, and they haven't been able to connect too much to climate change yet either. It's pretty difficult with tornadoes because it's just like small scale and a lot of factors involved. And for example, in 2021, in the prairies, I said that July is the peak month, and so for the 60 days in the summer, that is the peak season for tornadoes on the prairies. Initially, there were 0 tornadoes that occurred in 2021. We did end up finding 4 later on after going through satellite, but initially there were 0. And that probably was unprecedented. And it may be due to climate change because there were things going on to the west with heat domes, with drought, with wildfires producing smoke that drifted across the prairies and cut off the amount of sun getting to the surface. So what that indicates is that it's possible that climate change is going to reduce the number of tornadoes in some areas and increase it in others. And I think in the end, we're going to find that it's a very complex influence that climate change has, and it's going to be very regional in nature. Sometimes it's going to cause things to happen later in the year or early in the year, depending on the region. In the U.S., one thing they did find is that the number of tornadoes hasn't changed so much, but the number of tornado days has decreased, and there's just more tornadoes on those tornado days. So that kind of thing. It's very difficult to untangle all of these different things that are going on. But the first step in untangling things is good data, and that's what we're working on with NTP, is just getting the best data possible for them. As many tornadoes as we can across the country. I think I covered both parts of that.
Yes, you did.
Yes. Okay. Thanks.
Yeah, it is really difficult. We have so many intrinsic things to see on the data that you are collecting. So anyways, so I think I don't see any more questions on YouTube and here. So I have one more just to finish, maybe.
Sure.
On your derecho climatology, what data did you use? Satellite tracking, like what?
Oh, yeah, no, that was not easy. Mostly it was surface stations and reports in newspapers of damage and injuries and fatalities and that kind of thing. If we didn't go back too far, we still had access to some radar and some satellite. But when you get back more than 20 years or so, basically you're relying on old weather observations and old newspaper reports. And so there is a bit of detective work and a bit of art mixed with the science in doing some of this stuff. But it's not unusual when you go back in history to be able to do that. That's how a lot of the tornado databases and hail databases are put together, looking through old records and newspaper records and so on.
Yeah. Well, I have another one. It's just like curiosity.
Sure.
Do you have like a time frame for that community open source algorithms for nowcasting? That's very a great initiative. Very good idea.
Yeah. Well, they have a 3-year contract with us. The first year of the contract, which was 2022, was getting the processor and the viewer put together, and it was a big challenge for them, but it was done, and it actually works really great. It's, as far as I know, it's the only web-based app. All the rest of them are apps you have to load on your phone, but this is a web-based app. So it's independent of the iOS and different operating systems that you use, and you can actually open different windows as well for each radar, rather than with radar scope, for instance, you can only just open the one radar and look at that. That's it. So we're trying to make it so that it's it's much more useful for the community when we know that they're out there watching these storms across the country. We want to make it easier for them. But the next step in the contract is there are 3 steps. And the next step was to bring in lightning data, to bring in the warning data, some other observations, and be able to see for our field teams where they are relative to the other thunderstorms. So that's year 2. And then year 3 is building the tracking and severe weather algorithms and the nowcasting part of it. So yeah, there's a lot of work ahead of us, but they're really keen and they have some great developers on their team. So so far it's been great.
No, that's really, I'm looking for that. So, Bruno, you have more questions?
No, I think that's it. Yeah.
Okay,
Don't have more.
so thank you very much, Dave, for the presentation. I enjoyed a lot. And see everyone in maybe, in a month. We'll have another one.
All right.
All right. Thank you, everyone.
Thanks for the invitation. Take care.